not tie into each other. We are still using the same concepts from chapter 5 as what we have in chapter 4 already. Our primary focus in chapter 5 is basically your force of gravity. We're going to be, so there's two primary changes. The first one is we deal a lot more with force of gravity, because when we are doing the questions in chapter 4, usually your force of gravity and your normal force canceled out, right? So now we're going to look at examples where the force of gravity affects how something moves, okay? And then the second part of it, so force of gravity, basically what it says in the book here is called weight. So we are dealing with weight now. And I have already talked to you about the misnomer as to how we don't refer to weight properly. All right, when you ask somebody their weight, you're actually asking what their mass is, not what their weight is. Okay? The second thing that we're going to deal with more is force of friction. So all of the questions that you have done so far, all the force of friction was given to you at all times. So we're going to actually look at what happens when the force of friction is not given to you. What are the variables that are implied? Okay, so if you look at, just quickly peruse on the chart on page.
Mr. Newton, there was a question on the test where I had to find friction.
The force of friction. Yeah. On the environment.
Yeah, I understand. But I'm putting this in a different way. Take a look at page 163 and I'll explain it. Okay. Okay, so I mentioned this the other day. When we're driving a vehicle, most of you are starting to get your license now or have had your license for a while, but when you're driving a vehicle, there's obviously a glaring difference between when you're stopping on asphalt compared to when you're stopping on what we had to drive in yesterday with the snow on the ice, right? Yeah. Okay, so, exactly, right? So, depending on what the surfaces are that are reacting together, we can calculate what the force of friction is. Now, to get the force of friction, which is different than what, excuse me, the force of friction in this section, we're going to calculate it by taking the normal force and multiplying it by the coefficient of friction. And the coefficient of friction will either be given to you or you'll find it off of this chart on page 163. So what they've done for the coefficient of friction is they've compared how two surfaces rub against each other and what the frictional impact is on those two surfaces. Basically for us, you talk about rubber on concrete or rubber on asphalt, right? So dry, if the road is dry, you have a coefficient of friction of 1.07. The moment that it gets wet, your coefficient of friction goes down to 0.95. So what is that basically telling us?
You have lower friction.
You have lower friction when the road is wet.
Yeah.
All right? Then if you change it to rubber on ice, now look at the coefficient of friction, 0.005. So that changes drastically then, right? Okay? So that's the first thing that's going to be new to us, all right, in this section. The second thing that's going to be new is on page 156. So when we were talking about forces, we were only primarily talking about forces in which something sat on a surface.
Right.
But if we were looking at an elevator, okay, if I draw a free body diagram of an elevator, all right, what's the first force that acts on that elevator?
Gravity.
Force of gravity does, and it works straight down, right? But the moment you walk into the elevator, it doesn't fall.
No, that's applied force. It's a chain pulling.
Okay, very well said. All right? The only thing that we have incorrect on it is we don't refer to it as an applied force. You're absolutely right, it is. No, the normal force it won't change. It's always with the surface. We're going to call this force tension. Okay? So that force is the tension force. Okay? So it works exactly like an applied force. It works very much similar to what a normal force is, because it usually acts in the opposite direction of what gravity is, right? So now, if I'm looking at this question, is there any horizontal force on that elevator? Meaning, is it moving left or right?
No.
Now, unless somebody absolutely pushes it, which is not going to happen, clearly, right? There's no horizontal force in that question, right? Okay, so we can ignore it. So now, when I look at net force, here's the first way to look at it. When we've always talked about directions, we've always said up is positive, down is negative. But when it comes to forces, I'm going to look at this differently than what I have before. I am always going to place the force that's moving it in that direction as the first force. And anything that opposes it will be the secondary force. So for example, if this elevator starts in motion and it's accelerating downward, which force has to be greater, the force of gravity or the tension?
Well,
If it's moving down, it's accelerating, the force of gravity does, right? So the net force on that elevator is the force of gravity minus the one that's holding it back. So what's holding it up from falling? The tension. Okay?
wouldn't when it moves down, wouldn't that be an applied force? So, because that is
Or a release.
Yeah,
Like, because the tension's not stretching, it's like turning and letting the chain out more.
so that's like it applies it to the elevator. It
Right.
doesn't just
Or
No,
let
but
it go and let gravity.
I don't-
it's not like gravity's.
You're right. You're right. So basically what's happening is the force of friction of the cable, right, with the pulley, okay, is starting to lessen up, right? But if you actually think about it, what's actually happening is there's a cable that goes like this, and it's attached to a motor probably somewhere down here, or there's a motor at the top, in which if it's like this, then there's a pulley involved, correct? Or if it's just straight up and there's a motor, I don't think that ever happens. I don't think the motor is above. I think it's always on a pulley system. You want to know why it's on a pulley system? If you ever try and lift something up in the air, okay? Let's say you're sitting on the roof of your house and you want to bring something up that's fairly heavy, like a thing of shingles. Okay, let's say, hypothetically. All right? For you to reach down and pull them up, you're working directly against the force of gravity. Now, let's say I was actually standing on the ground and I wanted to get them up to the roof, okay? And I added in a couple pulleys. So it goes like this, the cable, right? Probably go down this way. You're down here, you're over here, so you're pulling on it right here, right? Okay? For you to lift that bag of shingles or that box of shingles or whatever up to the roof is going to take a lot of doing. But the moment you add in a pulley, it lessens the amount of tension on you and it allows you to pull something up. So if you actually look at an elevator, you happen to see an elevator shaft, your motor is still down on the ground for that elevator shaft and it's hooked up to pulleys. The reason that it's hooked up to pulleys is because it's easier to pull something using pulleys than it is to actually pull it straight up. Okay? We're going to look at that in a little bit. All right, we'll have a look at that and we'll explore that. Maybe that's something that we can take a look at. All right, now, so back to the question. Now, I'm only focused on basically the elevator itself,
Right.
the mass inside the elevator, whatever the mass is. Okay? Now, what would the net force be on this elevator if it's now moving up and accelerating in a positive direction? Sorry, don't let me say that again. If the elevator is accelerating going up, my net force then, what's the force that's moving the elevator?
That would be
Tension.
so it'd be
That's
T
tension.
subtract FG.
So all we're working with on this question, Brock,
oh
is
yeah,
tension
because
and force.
tension is just pulling. Yeah.
Right? And then what's holding it back?
Gravity.
Force of gravity. Okay? To make this less confusing for you as we go through these questions, the best way to look at every single question is, what is the force that's moving the object minus whatever the force is opposing the object. If you start getting into well, I'm saying up's positive and down's negative, you're going to mess up all of the signs on this.
Right.
The textbook's going to do that for you. All right, they'll do it. a different way. I think the easiest way to understand this concept in every single question is to say, all right, what force is moving this? What's opposing it? That's the easiest way to do these questions. Okay? All right, so let's have a look at this question in the book that they have here.
Sample problem.
Yeah, sample problem on 156. 75 kilogram man stands in an elevator. What will be the force the elevator exerts on him when the elevator is at rest? Okay. So the first thing I do is I draw out my diagram. I'm going to put my force of gravity this way. I'm going to put my tension force this way. Okay, so far? All right. 75 kg man stands in an elevator. Let's first find out what his force of gravity is. So how do I find the force of gravity?
Mass times gravity.
Okay, so let's do that. 75 times
9.
9.8. Somebody punch that into the calculator, please. Calculator's out.
175 times 9.8 or divided?
75 times 9.8.
735. 735.
735 newtons? Okay. All right, first things first. The question says, what will be the force the elevator exerts on him? All right?
Do we assume the elevator doesn't do anything?
For this question, yes.
Can't you go mass divided by acceleration? And it gets you your force.
But we don't have acceleration.
You got your force. It's mass times acceleration.
Uniform acceleration.
Acceleration is gravity.
Your acceleration is 9.8.
I thought the elevator is moving upward.
Not yet. It's not moving at all. Okay, so this goes back to this question then. If the elevator is at rest, what force is actually acting on this guy? Well, how do I find my net force? What did we learn in the last section?
Mass times acceleration.
Mass times acceleration. If the elevator is stationary, it's not moving,
So this is 0.
75.
so the net force on that is 0 newtons. Right? Because he's not moving. So far, so good? All right, now, here's the thing though. We know the net force is 0 on him. But what we want to do is we want to find out what the actual force is holding him up.
It's just the tension.
Right? So it's the what?
The tension.
It's the tension. And if the net force, okay, so we look at it like this. The net force is equal to, we know the net force is 0, we just solved that, right? So we got to go tension, and we can go minus force of gravity. Well, we calculated the force of gravity to be 735 newtons, didn't we? Correct? So I have tension minus 735. So if the elevator is at rest, what is the actual force of tension on that man?
735.
735 newtons. There's your answer to A.
And then you have acceleration.
Okay?
So because you're not moving, there's technically no direction that you're moving in. Would it change the question if you go FD subtract T?
No. Okay, so far? So in this question, if the net force is 0, that means that these two forces have to equal each other in order for that to happen. Okay, and direction doesn't matter. You could have put that as a negative, you still get it right. Okay? All right, let's look at B now. B says, now remember, the force of gravity doesn't change.
Still not.
So let me write that down. Force of gravity is still 735 newtons. Right? Because his mass times the acceleration of gravity. Okay, so now it says the elevator is moving upward with a uniform acceleration of 2 meters per second squared. So now we got to calculate the tension. So looking at my diagram again, the elevator is moving upward. Which has more tension? Or sorry, which has more force?
Tension.
The tension or the force of gravity?
Tension.
There's got to be more.
Still. And then in this case, it's going up.
It's going up. So because it's going up. So my mass, 75, times 2 is equal to my tension minus my force of gravity, right? Which is 735 newtons. So far, so good? Let's see. Okay, yeah. So what? How much tension is acting on that elevator then? 885 newtons. Perfect.
You add the two together?
How do I get T by itself if I'm subtracting 735?
Add 735 to 75.
Add 735 to both sides, right?
That's like what we were doing.
Okay, good. Now, does it make sense that the tension is greater than the force of gravity if the elevator is moving up?
Yeah.
Yeah.
Sure it does, right? Good. Okay, what about C? The elevator is now moving downward with a uniform acceleration of 2 meters per second squared. So this is what I'm saying. Rather than making the acceleration positive or negative, rather than doing that, I'm just going to rewrite my net force equation out. So in this case, which is greater, the force of gravity or the tension?
Force of gravity.
Force of gravity because it's going down. So that means that this has to be more force than that does, right?
Right.
So let's go force of gravity minus the tension in this case. Again, I'm still looking for tension though, right? Okay. So my net force is 75 times 2 equals 735 minus T. Looks very similar to what we just did, right? What's the difference now, though?
Minus T, or minus 735.
That's right.
Oh, yeah.
I have it's adding right now, right? So I got to subtract the 735 to that side. So I take 150, subtract 735, and what do I get?
585.
Negative. That's right. 585 newtons is equal to negative T.
Or flip it, like make them positive.
So I can make them both positive. So the tension in this case is 585 newtons.
Oh, okay.
Okay? Does it make sense that the tension force is less than the force of gravity here?
Yeah.
If it's moving down, if the elevator is moving down? Yeah. Okay? So far, so good? All right. Okay, we're going to get into pulley questions here. Okay. I'm going to show you one pulley question that we're going to start with, and then from there, I'll let you work on that assignment. So here's what's happening. The other day, we did a question in which we had a kid pulling little train cars, right? Remember that question? So you had 3 cars, I think it was. Looks something like this, and then he was pulling the 3 cars, right? I guess I'll just make that a force. So he was pulling the 3 cars. You remember this question?
Yeah.
What was it about the acceleration that we knew with the 3 cars?
Constant throughout.
Yeah, each one of the cars had the same acceleration because they were all attached, right? So they all moved basically as one. So then if I was trying to find the force here, I used that acceleration and I divided it into whatever the mass was here, right? Or times it by the mass to get that force. Correct?
Right.
Okay? I'm going to do the same thing today. It's going to look different, but I treat it exactly the same way. If I have a mass on a table, let's say that mass is 2 kg. I have a pulley set up. And I have a mass right here of 5 kg. Okay? Now, those 2 masses are attached by a string. And depending on the force of friction, because if the force of friction was great, was fairly high at where the 2 kilogram one was, all right, this guy wouldn't move, would it?
No, it'll outweigh gravity.
All right? Because the frictional force between the two and the table would be greater than the 5 kilograms pulling it down, right? Okay, but we're going to say that this 2 kilogram is on a smooth, frictionless surface. So there's no friction involved in this question. Fair enough? Okay, so I set this up as I have on the board here, and the moment I let go of this 5 kilogram mass, what's going to happen to it?
It's going to fall and the 2 is going to come with it.
It's going to fall, the 2 is going to come with it. That's very well said. That's exactly what I want you to get. It's going to fall, it's going to pull it down, and the 2 kilograms is going to go with, right? Because they're attached by the same string. Okay? So if I'm looking at the net force on this, the net force in this case then is what's going to start those 2 masses in motion?
Gravity.
On which one of the masses?
5.
On the 5. The 5 kilogram force of gravity is going to pull them down, isn't it?
Yeah.
Right? So this is going to be the force that's pulling them down. So the force of gravity on the 5 kg. Is there anything holding the 2 and the 5 kg masses back? Is there anything holding them right now?
Pulley and string?
No. They're frictionless as well. Sorry.
Oh,
Nothing is, right?
No.
The only thing that could hold these guys back, though, in theory, if it wasn't smooth and frictionless, would be some sort of friction right here. Would you agree?
Pulling the 2, yeah.
Right? That would be the only thing that could keep them from moving. Would be a friction, moving in this direction here. We call it that direction, so that's against it, right? But we'll worry about that after. The most important thing for you to understand right now is that those 2 masses are moving together.
Same.
So to calculate then what the acceleration of these 2 guys is, all right? Net force is mass times acceleration, right? Mass times acceleration. And this is force of gravity on the 5 kg. So I take 5 and I times it by 9.8. So I get 49 newtons here. Okay, so far? So force of gravity, 5 times 9.8, 49 newtons. Fair enough? Okay. How much mass is this guy actually moving? Is it moving just the 5?
no,
There's
it's moving the 2.
So it's moving 7. So I make my mass 7 here. So to calculate what the acceleration is on both of those masses, I take the 49 newtons and I do what? Divide it by 7. So how much acceleration is on them?
7 meters per second squared.
7 meters per second squared. So far, so good. Okay?
And that's if there's no friction.
That's if there's no friction. What would I do different if there was friction?
You would factor in the friction.
You'd subtract it from 49.
Absolutely. That's what I would do up here. I would just subtract the force of friction up there if there was.
Subtract from 49.
Okay?
That is not bad at all.
So again, we've done this already. The only difference will be that they're going to give you a coefficient of friction and they'll tell you to solve for what friction is. But other than that, it's the same thing we've already done.
And the coefficient would be like 5, right?
No, the coefficient will be given to you. It'll be a decimal. Like very similar to those numbers on that chart. All right, fine. Here's the thing though. What we want to do though, all right? So far we've followed this along really well, right? Okay. What if I looked at just the individual masses? What are the forces acting on the individual masses? Okay, so let's ignore this 2 kg for right now. What are the 2 forces affecting the 5 kg?
Gravity.
Gravity and
Tension.
tension. That's right. And tension would be right here, and that's where the rope comes into it, right? There'd be a tension force there. Agreed? Okay, so the net force on the 5 kg 5 kg one is the force that's moving it in the direction that it's going, which is
Down.
down. What's that force?
Gravity.
Gravity. And what's the force that's holding it back?
Tension.
Tension. Okay, so far? Now remember, I'm ignoring this 2 kg for a second. Ignore the 2 kg. All right? I'm just dealing with this 5 kg. We know what the acceleration of that 5 kg is. It's 7. Right? So I go like this. I go 5 kg times 7 meters per second squared is equal to 49 minus t. So now what I want to do is I want to calculate what the tension is in this question.
Negative 14.
All right, so I'm going to get negative 14 newtons here. That's going to be what negative t is. So what is t?
14.
14 newtons. Okay? So the tension in that string between those two masses is 14 newtons. Fair enough so far?
Would your acceleration be different if you were only looking at the 5? Like, instead of 49 divided by 7, it'd be 45 divided by 9? Or divided by 5, sorry?
No. Okay. No. All right. I want you to ignore the 5 kg for 1 second. I'm going to show you something real quick here. You can get these questions right and prove your answer very quickly. Let's ignore the 5 kg right now. What are the forces acting on the 2 kg? Again, ignore that. What are the forces acting on the 2 kg? Go ahead.
Force of gravity and the normal force.
Force of gravity, normal force. And what happens with those two? They
Cancel each other.
cancel out because you're on a horizontal surface, right?
Right.
All right, so what's the force that's going to move that 2 kilogram mass then?
Force of tension.
Tension.
Mm-hmm.
Tension is.
Mm,
What's holding that 2 kilogram back from moving?
friction.
Something.
In
Well,
this case,
nothing.
nothing, because there's no friction, right? There's nothing to hold it back. So then, if I'm looking at just this mass right here, the only thing affecting it is tension, right? Only thing affecting is tension. So the net force on it is actually my tension force. My mass, 2. What's the acceleration of that 2 kg when I let the 5-1 go? 7. Equals tension. How much tension do I have on there? 14 newtons. That rope is the same rope on both of those masses. Therefore, when you calculate the tension in the rope, it should be the same for both. This is actually the easier way to get it. This was a little bit harder. But that's it. Okay, so far are we all right? So what you're going to find, what I'm going to do, and you can't follow the book in this, so I would probably, just a suggestion, I would have wrote this all down, but this is why you guys are not getting your answers right on your sheet, because you're not writing any of this stuff down ever. I give you examples, you have to put this in your book. You have a worksheet to do in which you need examples for, and it's right here. Okay? But for this guy right here, the book is not going to do it this way. The book does it a little bit more confusing way. This is the easiest way to do it. Find your acceleration for both of them first, and then find the individual tensions after. That's the easiest way to do that question. Okay, one more quick note, and then I'll let you go. Just want you to have a look at this. What would happen if I had 2 hanging? Let's say I had a 2 kilogram one hanging here, and a 5 kg one right here.
It would pull the 2 right over top.
You'd pull the 2 right over the top?
Force tension pull.
Okay, now remember, the rope for right now is attached to both, correct?
Yeah.
The rope's attached to both. So all I'm looking back at is the 2 of them together as a system. So if I ask you what the net force is on this, which force is going to move them and why?
Gravity.
Gravity on which one? The 5. Because of the larger mass, it's going to go in that direction, right? So the force of gravity of the 5 is going to move them. Which force is going to hold them both back?
Tension of 2.
No.
Gravity of 2.
Force of gravity on the 2. If you look at it like this, which way is this guy going? Well, he's going that way, right? Which way is this guy going? Well, he's going that way as well.
It's not gonna after you let 5 go.
Exactly. Then larger mass is going to take over in this case, and it's going to force it to go in this direction. But when I look at them together as a system, as a unit, as a train that's hooked together, the 5 kg is going to move both of them. The 2 kg is going to try and resist them a little bit. Okay? Right? This whole chapter 5 section is exactly the same as chapter 4, with just this in it right here. So the potential for you to do well on it is there if you put the work in. Okay? That's all I have for today. If you finish your assignment, you can look at the page 158 and 161, those 6 questions. They won't take you very long. All right? Again, I can't stress that enough, boys. You guys aren't copying stuff down off the boards. It's good to follow, which is what I want, and be involved, but when it comes to this assignment, you should have had all of these down. Sorry.
What did I do?
Cost you agent, that.
If I have any notes, I take everything down. Keep it on.
You need that math test too?
Yes.
You finished that math test. You finished, you said you wanted to look at it again, right? Thank you. Yeah.